Good afternoon, students. It is so good to have you for lecture 4 for General Chemistry 1. Chemistry 127N. It is so good to have you. So good. So I hope everyone's doing well. So let's begin with the lecture for today. The introduction, these are the main tenets or the main ideas that I want you to keep in mind as we go throughout this lecture. Let's talk about the first section. Electronic structure of an atom describes the energies. So we know that energies are quantized, and Planck's equation gives us an insight into that quantized energy. And the arrangement of the electrons, which Bohr described, Schrödinger explained, all of those things around the atom. Much of what is known about the electronic structure of atoms was obtained by observing the interaction of light with matter. We saw this with the Young split experiment, and also with atomic emission spectra. Visible light and other forms of electromagnetic radiation, whether you have your gamma, your X-rays, your ultraviolet, your visible light, your micro, your infrared radiation, and your radio waves, that's it from high frequency to low frequency. Electromagnetic radiation moves through a vacuum at the speed of light, 3.00 times 10 to the 8 meters per second. Electromagnetic radiation has both electric and magnetic components that vary periodically in wave-like fashion. The wave characteristics of radiant energy allow it to be described in terms of wavelength, lambda, and frequency, nu, which are interrelated. C, which is the speed of light, is equal to the lambda times nu. So lambda times nu equals C. Okay, section 2, we'll talk section 2 in the book deals with Planck's equation. And we know Planck's equation is E equals h nu. And what Planck basically described, he gives the idea that the minimum amount of radiant energy that an object can gain or lose is related to the frequency of the radiation. E equals h nu. The smallest quantity is called a quantum of energy. The constant h is called Planck's constant, and Planck's constant is equal to 6.626 times 10 raised to the minus 34 joules per second, joules times second, so joules second. In the quantum theory, energy is quantized, meaning that it can have only certain allowed values. Einstein used the quantum theory to explain the photoelectric effect, the emission of electrons from metal surfaces by light. We explained that, in which you have light shining on a metal surface, that the frequency of light results, or the energy associated with that electromagnetic radiation results in the excitation of the electron and it being emitted, because the energy that it releases, or the energy associated with the electromagnetic radiation, overcomes the binding energy of the electron, resulting in the emission of the electron. Hence, you have the photoelectric effect. He proposed that light behaves as if it consists of quantized energy packets called photons. That's where we get the idea of photons from. Each photon carries energy E equals h nu. So Planck's equation and Einstein's idea of the photoelectric effect coincides well. Then we have dispersion of radiation into its component wavelengths. It produces a spectrum, and we understand that a continuous spectrum is like a rainbow. It consists of all of the wavelengths. It's a continuous spectrum of light in the visible region. That's what a rainbow is. It is called a continuous spectrum. If it contains only certain specific wavelengths, the spectrum is called a line spectrum. And we see this with AES, or atomic emission spectra. The radiation emitted by excited hydrogen atoms forms a line spectrum. The frequencies observed in the spectrum follow a simple mathematical relationship that involves small integers. Bohr proposed a model of the hydrogen atom that explains its line spectrum. In this model, the energy of the electrons in the hydrogen atom depends on the value of a number n called the quantum number. The value of n must be a positive integer, 1, 2, 3, or other integers, and each value of n corresponds to a different specific energy, En. And we see the value, or we see the notation of n in the Rydberg equation, which is 1 over lambda equals the Rydberg constant in brackets 1 over the final state, or nf squared, minus 1 over the initial state, or 1 over ni squared in brackets. And that gives you the values for the energy associated with transitioning from one stationary state or one quantized state to another. Bohr proposed a model of the hydrogen atom that explains its line spectrum. That's why his model was so important. In this model, the energy of the electron in the hydrogen atom depends on the value of n. And also, one of the things we understand from Bohr's model is it addressed the hydrogen atom well. However, it didn't really address other atoms as well. And then it also didn't address the phenomena or the occurrence of what happens whether or when an electron was to fall into the nucleus. It didn't address that. However, in the classical paradigm, that typically does not occur. So, section 6.4, we now talk about wave-particle duality with de Broglie, in which he basically said that matter has both wave-like and particle-like property. Hence, we have the duality of waves and particles, or wave-like and particle-like properties. His hypothesis of matter waves was proven experimentally by observing the diffraction of electrons, and this occurred with the Davis-Germer experiment, in which the diffraction of electrons as they pass through a crystal of a metal. And it also we talk about Heisenberg uncertainty, in which we basically say there's an inherent limit to the accuracy in which we can know, or by which we can know, the position and momentum of a particle. There's an inherent limit. So either the more you know about, another way to put it is the more you know about the position, the less you know about the momentum in terms of a particle such as an electron. Heisenberg uncertainty, it points towards basically the idea that quantum mechanical behavior does not translate exactly into macroscopic observations. What does all that mean? It means that, because for example, Heisenberg uncertainty is negligible for atoms, or for not for atoms, for substances or for objects such as a tennis ball. There's no uncertainty in terms of its position and momentum. You can determine those things with a great degree of accuracy, or there's less uncertainty, negligible uncertainty. That's a better way to put it. But for an electron, there is uncertainty, and hence we have this quantum strangeness. Hence we have this wave particle duality. It's just there's a lot going on, and that's why we have to look at Schrodinger's equation, in which he explains the behavior of electrons, the behavior of atoms using wave functions. And from those wave functions, we also understand that those wave functions give us an idea. It gives us an idea in terms of the probability density, in which you know the specific location of an electron for a point in or on the atom, and then you have the radial density, in which you know the location at any point. So probability density is a more specific descriptor. Radial density is more general. Then you also know n, m sub l, l, m sub s, n, the principal quantum number, and that gives you an idea of the energy associated with the orbital, how large it is. And then you also have L, which is the angular quantum number, which gives you an idea of the shape. And then you also have M sub L, which gives you an idea of the orientation of the shape of that orbital. And then you also have M sub S, which gives you an idea of whether the electron is spin up or spin down. So all of these ideas are giving us better and better and better descriptions of the electrons in the atom. Now, different representations, whether it be the radial probability function or the probability density function, these ideas. And then from there, we proceed on to principles, whether it be Pauli's exclusion principle, Hund's rule, or Aufbau principle. Pauli's exclusion principle basically states that no two electrons can have the same four quantum numbers. And what are those four quantum numbers? N, L, M sub L, and M sub S. Or the principal quantum number, the angular quantum number, the magnetic quantum number, and the spin quantum number. It cannot have the same four. We also understand Hund's rule, in which when you are filling degenerate orbitals, electrons fill them singly first with parallel spins. And then we also have Aufbau principle, which is derived from the German word to build up. And that's just explaining how you fill degenerate orbitals. And then we also talk about so one of the things we get from the Bohr's model, from Bohr's model, is it also gives us an insight, or it coincides well with the periodic table, um, because when you are doing filling of orbitals, if you look at the periodic table, it follows this observation: 2, 8, 8, 18, 18, 32, and 32, and that's for electron counting. But we'll get to that later. But it coincides well with some of the earlier ideas that you learn in PGCSE chemistry when writing electron configuration. So that's a general overview of what we will discuss today. So let's begin. Let's begin. Okay, view. Okay, so as I said earlier, I'm a young faculty at the University of Bahamas. And I want everyone to remember, you are not alone. This is an academic community. Remember to get help when needed. Reach out to university services if needed. Never give up. Keep trying. We are here to help you be ethical, intelligent, and responsible and successful scientists. However, at the end of the day, ladies and gentlemen, you must be responsible, ethical, and hardworking. This is just a shout out to your boy, Werner Heisenberg. He did his postdoctoral assistantship. So after his PhD, he did some training with Niels Bohr, the person who came up with the Bohr model. Isn't that something? That's very interesting. That's a very good job that he got. Heisenberg formulated his famous uncertainty principle during that training period. So he was working with a great scientist, and that led to him becoming an even greater or an equally as great scientist. It's interesting to note that at the age of 25, he became the chair in theoretical physics at the University of Leipzig. That's in Germany or in Eastern Europe. At 32, he was one of the youngest scientists to receive the Nobel Prize. That's very commendable, very commendable. So, keep track of your work, keep track of your assignments. Remember, the goal of this class is to teach the chemistry content in an engaging manner that is relevant to the Bahamian student and digestible for their understanding. The sequence is as follows: understand the fundamental concept, practice problems related or relevant to understanding that fundamental concept, learn more nuanced details about the fundamental concept, and practice more complex problems that integrate the details and the fundamental understanding. So a practical example of this is we look at the Bohr model. We practice problems or we do the pictures in the workbook with the Bohr model. Then we learn nuanced details in which Bohr model leads to an understanding or helps us understand what Schrödinger was trying to work on and how Schrödinger's equation is so significant because it not only explains the structure or the properties of the hydrogen atom, but it also explains, using the computational power that we have today, it explains the behavior of many multi-electron atoms. And that is a nuanced detail. And then we practice more problems. And those problems can involve Rydberg's equation. All those problems can involve looking at quantum numbers. All of these things they build. That's why it's important to stay on top of the things in class and understand the material and listen to the YouTube lectures and the podcast so that you can have multiple opportunities to get the content. So we are in week 2. My goal, as I said earlier, is not to overwhelm anyone, but to help you understand the content well. So de Broglie's work, let's break it down. Break it down. Okay, so de Broglie's equation is stated as lambda is equal to h over mv. And his equation relates the wavelength of the radiation, the wavelength of the thing you're looking at, the wavelength of the particle to the momentum of the particle. It relates wavelength, mass, velocity, and Planck's equation. I mean Planck's, yes, Planck's equation, but Planck's constant. That's the thing that it really relates. We understand that de Broglie's work is applicable to all matter. All matter of mass m with velocity v would give rise to characteristic wave-like particles, wave-like properties. Hence, we have wave-particle duality, in which you have wave-like characteristics and particle-like characteristics existing at the same time for the same particle. And this was proven experimentally with the electron, particularly with the Davis-Germer experiment. Um, so I'm going to proceed, but just remember that different types of reactions. It's important to know those, whether it be addition, decomposition, single displacement, or double displacement. An example of addition would be the formation of an ionic compound from a cation and an anion. An example of a decomposition reaction is the formation of electrolysis, or the result of the reaction, electrolysis reaction, of water into hydrogen and oxygen. An example of a single displacement reaction is an SN2 reaction in organic chemistry, and an example of a double displacement reaction is a precipitation reaction. It's important to understand these ideas. I already went through an overview of the content. The skills I want you to know. I want you to be able to calculate wavelength of EM radiation, given its frequency, or its frequency given its wavelength. I want you to understand the common kinds of radiation, from gamma radiation to radio waves. I want you to understand the concept of photons. And we understand the concept of photons because Einstein described how energy and EM radiation is quantized and exists in particles or quantized amounts called photons. I want you to understand and explain the ion spectra, and the Bohr model coincides well with that. I want you to be familiar with the wave-like properties of matter, and de Broglie's ideas coincide well with that. I want you to understand uncertainty principles, the uncertainty principle, and Heisenberg uncertainty, which specifically refers to the fact that the more we know about the position of an electron, the less we know about its momentum. We cannot know about those things with the same degree of accuracy in the same instance. I want you to understand radial probability functions, which basically describes where the electron is at any point in space in the atom. I want you to understand energy level diagrams, Pauli's exclusion principle, in which no two electrons can have the same four quantum numbers, Hund's rule, in which when you fill in degenerate orbitals, you fill them singly first with electrons, and those electrons have parallel spins. You see this example of this when you fill in p orbitals initially for the first three electrons. I want you to be able to use a periodic table to write abbreviated electron configurations from the S block on the right, on the left, to the P block on the right, to the D block in the center, to the F block below, SPDF, which are descriptors or designated letters that coincide very accurately with the angular momentum values, whether it be 0 for S, L equals 0 equals S, L equals 1 equals P, L equals 2 equals D, and L equals 3 equals F. Those are the designated things. I want you to understand those things. And SPDF, they just come from the descriptions of the terms of the words sharp, principal, diffuse, and fundamental. So let's talk about the characteristics of electromagnetic waves. Electromagnetic waves, like most waves, they have wavelength, they have a frequency, they have amplitude, they have crest, they have trough, they are transverse waves. They propagate in a horizontal and also a vertical direction. Yes, you have your different types of radiation. You have your gamma rays, your X-rays. I hope you see, as you look at this diagram, that where the frequency is 10 to the 20, gamma rays, the wavelength is 10 to the minus 11. And as you increase the wavelength, the frequency decreases as you move from left to right. As you increase the wavelength, the frequency decreases. So although the wave model is a description of light, several phenomena need to be explained. The emission of light from hot objects, black body radiation, and Planck's equation does a good job with explaining that. The emission of electrons from the metal surfaces, and Einstein's ideas with the photoelectric effect do a good job of explaining that. And then the Bohr model explains tenet 3, or caveat 3, in which you have the emission of light from electronically excited gas atoms. And that occurs, or that we understand the phenomena by observing emission spectra. So key principles to know. Werner Heisenberg came up with the Heisenberg uncertainty principle, and that was very important, very important. Let me show you a picture of Werner before we proceed. Werner. Yes, Werner Heisenberg at the beginning of this reaction. That's the person we're talking about. Okay, there we go. Werner Heisenberg came up with Heisenberg uncertainty principle, in which the more we know about the position of an electron, the less we know about its momentum. The more we know about the change in position, the less we know about the change in momentum. We cannot know them with the same degree of accuracy in the same instant for an electron. Pauli's exclusion principle, in which no two electrons can have the same four quantum numbers. Hund's rule, in which when you're filling degenerate orbitals, electrons fill them singly first with parallel spins. The Aufbau principle, when you're building up or when you are drawing electrons in degenerate orbitals, you build it up from S to P to D to F. And wave-particle duality, in which de Broglie's ideas explain that matter has both wave-like and particle-like properties, and that was observed experimentally with the electron with the Davis-Germer experiment. Okay, Planck's theory of matter. Planck's theory of matter basically stated that matter is always allowed to emit and absorb energy only in whole number multiples of h nu, such as h nu, 2h nu, 3h nu, and so forth. If the quantity of energy emitted by an atom is 3h nu, for example, we say that 3 quanta of energy have been emitted. E equals h nu. So this would be a good time to practice the questions on the homework associated with Planck's equation. So photoelectric effect. Here we see an example of radiant energy hitting the metal surface, the electron being emitted, it's picked up by a positive terminal, the voltage source transmitted, and we observe the reading on the current indicator, which is it shows you that you have an electron passing through the wire. So yeah, Einstein observed this phenomenon in 1905, creating a spectrum. Key thing to keep in mind here are the components. So even for a rainbow, you have a rainbow, the sun is your source of light. The basis on which dispersion occurs is through the water droplet. And then you have your continuous spectrum, when you have several of those water droplets. And as you see, the more light is dispersed and the same degree of dispersion occurs, we can have a larger and larger continuous spectrum. Hence, we have rainbows in the sky that's seen by multiple observers. But when we're doing that in the lab, we have a light source, we have our slit, we have our prism, and then we also have a black screen or some filter or something that will show us the continuous spectrum. A continuous spectrum shows you all of the wavelengths. And for a rainbow, it's all of the wavelengths in the visible region of light. However, a discrete spectrum or a line spectrum gives you a spectrum containing radiation of only specific wavelengths. A continuous spectrum, as I said earlier, consists of all wavelengths of light in a specific region of the EM radiation spectrum. Atomic emission spectra shows you an example of line spectrum, in which you have specific wavelengths being produced as shown by the colored lines. See at the bottom there, hydrogen spectrum, and Bohr's model does well to explain hydrogen spectrum. Schrodinger's equation explains basically all spectra well, especially with the computational power that we have today. So the Bohr model. Bohr's model was based on three postulates. Only orbits of certain radii corresponding to certain definite energies are permitted for the electron in a hydrogen atom. An electron in a permitted orbit has specific energy and is in an allowed energy state. An electron in an allowed energy state will not radiate energy and therefore will not spiral into the nucleus. These are Bohr's postulates now. Bohr's postulates. So you keep the context in mind. Also, energy is emitted or absorbed by an electron only as the electron changes from one allowed energy state to another. This energy is emitted or absorbed as a photon, E equals h nu. So just to drop a little idea, there are allowed states and there are forbidden states, but we're going to get into that in this class. You could deal with that in a quantum physics or theoretical physics or theoretical chemistry class. This is a good point to practice equations, practice questions rather, on Rydberg's equation, where lambda is the wavelength, r is the Rydberg constant, and f is the final state or final position of the electron, and n equals n sub I is the initial position of the electron. So Bohr's model is a good thing to map this equation onto, where NF could be the final uh, discrete or quantized the circle. The circle. So you say you have three circles. Where's the first your first energy level, or your first quantized state, and then the second and the third. So you have your three circles. For example, with the sodium atom, if it goes from n equals 2 to n equals 3, 2 would be there, 3 would be there. You square them, you get your value of the wavelength that is associated with that electron going through that transition from one energy state to another, allowed energy state to another. The Bohr model has limitation. It only explains the line spectrum of the hydrogen atom well. It avoids the problem of a negatively charged electron falling into the nucleus. So hence we have, or here we have, de Broglie's ideas. And the classic example of that is with a water wave. A water wave has wave-like properties, and it also has particle-like properties because it's made up of units, which are water molecules, or particles, which are water molecules. De Broglie further extended the ideas of Bohr. He postulated about matter's properties. If radiant energy could behave in a particle-like way under appropriate conditions, could the electron be thought of as having wave-like and particle-like properties? So hence we go, this is the first tenet, or first principle that I'm responsible to teach you for this class. So we will understand that de Broglie's work is applicable to all matter. All matter of mass m with velocity v would give rise to characteristic wave-like properties. Hence we have wave-particle duality. De Broglie published his theory, and within a few years, the wave properties of the electron were demonstrated experimentally, not occurred with the Davis-Germer experiment. So let's keep going. So we're going to talk about, as I introduced earlier in lecture on Monday, I introduced, let's see, I introduced that is associated with quantum numbers. But before we get to that, I will pause the video for a bit. I would recommend you pause the video for a bit, recap, take notes, practice problems, and then jump into this section of the video. Okay, so let's continue. Big ideas. All matter is made of atoms which can be understood with their subatomic particles. Chemical reactions involved in the rearrangement of matter and the atoms that make up chemical reactions are involved with the rearrangement of matter and the atoms that make up that matter. Each chemical reaction is dependent on rate, equilibrium, atom proximity, and orientation. These are big ideas. These are the tenets, the principles, the main ideas we want to know and understand well this semester and next semester. Force is either intramolecular, so bonding, so covalent or ionic or dative or dative bonding, or intermolecular, your H bonding, London dispersion forces, all of those things. Explain the properties of the substance. Dipole-dipole interactions, intermolecular bonding, all those things. Van der Waals interactions. And then 5, equilibrium, rate, atom proximity, and molecular orientation in a chemical reaction are mathematically related. So, the names of the scientists in science history are Albert Einstein, Niels Bohr, Louis de Broglie, Max Planck, Werner Heisenberg, Paul Dirac, and Erwin Schrödinger. These scientists made tremendous contributions to physical chemistry and physics, from Einstein's theory of relativity and the study of the photoelectric effect to Heisenberg's uncertainty principle. All these ideas are useful in science today. Schrödinger's equation describes the behavior of electrons in the atoms. It gives us information to transcribe the electronic configuration of atoms with the periodic table as an aid. So the goal was to Bahamianize quantum chemistry. Erwin Schrödinger was a Nobel Prize-winning Austrian-Irish physicist who worked on developing key ideas in quantum chemistry. His equation allows for the calculation of eigenstates of a system as well as dynamic changes in time. Erwin Schrödinger spent most of his life as an academic, winning the Nobel Prize in 1933 along with Paul Dirac. Very intelligent person. Schrödinger's wave equation discovery occurred in 1926, and it came about from being convinced that atomic spectra should be derived from eigenvalue problems. Here we see an example of Schrödinger's equation. So, um, let's continue. Schrödinger's equation results in many solutions, and each wave function has a corresponding orbital associated with it. The orbital and the respective electrons are specified by 4 quantum numbers. Hence, listen to the operative word, specified. These are specified descriptors. So we have the principal quantum number, the angular quantum number, the magnetic quantum number, and the spin quantum number. So Schrödinger's equation is H psi equals E psi, where H is the Hamiltonian. These are just mathematical operators. Don't get lost in the details. The main idea to remember is his equation. Initially, or when he first came about, it worked well for the hydrogen atom. But when computational power was revved up, as we have today, it basically explains all the behavior of all atoms. That's a powerful equation. It gives us insight to chemical reactivity and all those things. But the 4 descriptors I want you to keep in mind are the principal quantum number n, the angular quantum number L, the magnetic quantum number m sub L, and the spin quantum number n sub S. The principal quantum number is an integer value that describes the overall size and energy of an orbital. The energy associated with the orbital is negative because the electron's energy is lowered via Coulombic interactions with the nucleus. Orbitals that have higher integer values for the principal quantum number have energies that are less negative. Moreover, as the principal quantum number increases, energy changes between the subsequent energy levels typically is less. And that ties into ideas of penetration and shielding, but we haven't reached there yet. Because I'll just give you a quick hint into what that's referring to in terms of energy changes between the subsequent energy levels typically is less. Coulombic interactions result between particles of opposite charges result in lower potential energies. So if you have low potential energies due to penetration of those orbitals nearer to the nucleus, that's going to result in you having subsequent energy levels with energy changes that are less. So let's talk about L. The angular momentum quantum number is an integer that describes the shape of the orbital values from 0 up to n minus 1. So L equals 0 equals S, L equals 1 equals P is designated as P, L equals 2 is designated as D, and L equals 3 is designated as F. The magnetic quantum number m sub L is an integer value that provides information on the orientation of the orbital. The possible values of m sub L range from minus L to plus L. M sub S, the spin quantum number, specifies the orientation of the spin of the electron. Electron spin is a fundamental property. The spin quantum number has 2 possible options, spin up or spin down. The energy orbital S typically is shown as a spherically symmetrical low energy orbital. The 3D image is a plot of the wave function, which describes the likelihood or probability of finding an electron at a position in space. And it's from these wave functions that we go to or we walk towards our radial density radial distribution function and a probability density function. The probability density function, which describes the probability in terms of volume of finding an electron at a specific point in space. The atomic orbital can be represented with a 3D geometrical shape, and we understand that shape from our angular quantum number, and that shows the volume of the electron that's likely to be found most frequently. For an alternative explanation, you can use the radial distribution function, which provides information on the total probability at a radius r. So for some radius r, it gives you the idea or it gives you insight into the position of an electron at any point in space at that radius r. The function has a value of 0 at the nucleus, so theoretically you shouldn't find any electrons at the nucleus. The positive charge is posit at the nucleus. So we've already discussed Schrodinger's thought experiment. The thought experiment points to the idea of strange behavior in quantum mechanics does not directly transfer macroscopically. Hence, we could have Heisenberg uncertainty with the electron, but Heisenberg uncertainty is negligible for something like a tennis ball. Let's talk about Schrödinger. He was an assistant to Max Wein in 1920, followed by other pivotal academic positions. His tenure at the University of Zurich, working along with Louis de Broglie, that's the person who came up with wave particle or gave us ideas of wave particle duality, with his equation lambda is equal to h over mv, or Planck's constant over the momentum is equal to the wavelength, and it proved valuable to his academic career. In 1927, Schrödinger left to function as an academic at the University of Berlin. It was during his time that he received the Nobel Prize along with Paul Dirac in 1933 for his work in theoretical physics. Quantum mechanical theory describes the behavior of electrons and atoms. It also aids in our understanding of an electron configuration. An electron configuration for atoms shows the particular orbitals that electrons occupy for that atom. Electrons generally occupy the lowest energy orbitals available for atoms in their ground state. The analytical complexity occurs with Schrödinger's equation for multi-electron atoms. Hence, this is the reason why we needed more computational power to solve Schrödinger's equation for multi-electron systems of multi-electron atoms. When attempting to understand concepts associated with quantum mechanics, two concepts need to be considered heavily: the effects of electron spin and sublevel splitting. Electron spin is a fundamental property of all electrons that affects the number of electrons permitted in any one orbital. In terms of sublevel splitting, this describes the order of orbital filling within a level. Energies of sublevels are split. In general, the lower the value of L within a principal energy level, the lower the energy E. It is as follows. The energy of orbital S typically is less, or theoretically is less than energy of orbital P, which is theoretically less than energy of orbital D, and the energy of orbital D is theoretically less than energy of sublevel F. So these are sublevels that we're referring to. It is important to understand Coulomb's law, shielding, penetration, effective nuclear charge, and other ideas that we will discuss later. So I want you to remember that the logical consequences of Coulomb's law is it's like a pillar for many of these concepts that we're discussing. Or it's like a side pillar for some of them, and it's a main pillar for many. Like charges repel. As the distance decreases between like charges, the potential energy increases in magnitude for those like charges. Unlike charges have more negative or less positive potential energy as the distance between those unlike charges decreases. Also, the magnitude of the potential energy interaction is proportional to the magnitude of the charges interacting. So we won't discuss shielding at this time. That's something I will discuss later. As consequences, this is just a picture of Einstein's dissertation. The beginning page of his dissertation is in German. He did his PhD at the University of Zurich. So it's on the new determination of molecular dimensions. If you have any questions, you can ask me about that in class. I'm not going to discuss the dissertation on this lecture. So these are the electron configurations of the first 20 elements. Keep this in mind. I'm just exposing you to these ideas. We will discuss this in detail in class. And these are the shapes. So L gives us an idea of these shapes. L equals 0 refers to F, L equals 1 refers to P, L equals 2 refers to D, and L equals 3 refers to F. So in relation to the photoelectric effect, it was observed that metals emit electrons when light shines on them. Einstein and Max Planck were some of the first scientists to suggest that energy is quantized. There's a task for you to look into. I want you to go and research the Nobel Prize in Physics for 2018. Draw and explain the interference pattern from two splits and explain how that relates to Young's double slit experiment. Those are assignments for you students to do. According to classic electromagnetic theory, the photoelectric effect occurred due to the transfer of energy from light to an electron in the metal, resulting in the dislodgement of the electron. Some of the key equations to know are E equals h nu, or E equals hc over lambda, where E is energy, h is Planck's constant, v is frequency, and c is the speed of light, and lambda is wavelength. So Albert Einstein's idea that light is quantized starts to provide a good framework for the photoelectric effect. The equation for the kinetic energy of the electron is Ke sub Ke of the electron, the kinetic energy of the electron, is equal to h nu minus psi, or phi rather, and that phi is referring, or is representative of, the binding energy. So I want to discuss this idea. It is possible to separate light into a series of colorful lines that we call emission spectra. The spectrum for a particular element is characteristic of that element. Johannes Rydberg was a Swedish mathematician who analyzed several spectra and developed an equation that predicted the wavelength of the emission spectrum for hydrogen. Let's talk about your boy, Niels Bohr. He was a Danish physicist who worked, researched, and developed ideas that led to a model aimed at explaining atomic spectra. In the Bohr model, the orbit exists only at specific fixed distances from the nucleus. The idea of stationary states in the Bohr model has origins in the wave nature of the electron. With an understanding from the Bohr model, we can describe the spectral lines as a result of when an electron falls from a stable orbit to a lower stationary state or orbit. Here we have Rydberg's equation, and this is Rydberg's constant. His constant is minus or negative 2.18 times 10 raised to the minus 18 joules. Rydberg's work on equation, which equates wavelength and orbital energy states, helps us understand atomic emission spectra. Bohr's model further described that only transitions result in radiation being emitted. When, as the cartoon describes, when electrons relax after being excited, is because the relaxation releases energy which corresponds to a particular frequency of light that is directly related to the color of light that is emitted. So these are things that I didn't mention in class, but these are emission spectra. They were also studied, or spectral series were also observed and studied, and equations were derived by other key players such as Lyman, Paschen, and Balmer, in which you have different series associated with those names. Now let's talk about your boy, Louis de Broglie. He lived from 1892 to 1987 and helped develop the root of quantum mechanical theory. So as you see, as we go along, I want you to see, yes, there are 7 big names that we discussed earlier, or 7 big names I mentioned earlier: Albert Einstein, Max Planck, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Max Planck, all of those things, all of those people. I just want you to keep in mind that everybody, whether it was a linear combination of work, everyone contributed to the quantum mechanical theory that we understand today. It took many hands to make this work occur, this progress occur. His theory, de Broglie's work, his dissertation, posited or discussed the wave nature of electrons. So just one distinction quickly to make. Sound is not an electromagnetic wave, it is a longitudinal wave. Sound requires a medium to propagate. Light is a transverse wave, and it can propagate in a vacuum. So according to de Broglie's wavelength, a single electron in motion in space has a wave nature due to its kinetic energy. The de Broglie equation, lambda equals h over mv, where h is Planck's constant, m is mass, and v is velocity. So this is the 1927 experiment that I kept on referencing, Davison and Germer. It basically described the observation of electrons undergoing diffraction by a metal crystal. And these ideas help to prove experimentally the ideas of de Broglie. So just keep that in mind. The wave and particle nature of an electron is not easily understood, and this makes a path for the uncertainty principle. As alluded to in the thought experiment, the unobserved electron can occupy 2 states, but the act of observation forces it into one state or another. Upon observation, we understand it to be either occurring as a particle or as a wave. A Young's double slit experiment points well to this idea, and it is something we will discuss in class later. So it is known that de Broglie did some work at the Poincare Institute establishing an analytical or applied science department, Center for Applied Mathematics. And I cannot forget to mention Max Planck, the law of work on EM, electromagnetic theory, electromagnetic radiation. His work laid the foundations for quantum theory, and he won the Nobel Prize in Physics in 1918. So these are your boy, Max Planck and Werner Heisenberg. They also published papers with leaders in the field such as Max Born, the Born-Oppenheimer approximation. You keep just think about that. And Pascal Jordan, you have if you discuss or look into linear algebra, you see Jordan. But these are just people you want to keep in mind. Just keep them in mind. Good to know. Here we have an example of Heisenberg uncertainty principle in a mathematical description, mathematical format. Helps us understand. He also introduced the ideas of complementarity, in which electrons observe either the particle or wave, but not at once. And let's rehash these things. Wolfgang Pauli came up with Pauli's exclusion principle. It states that two or more identical particles with spin cannot occupy the same quantum state in a quantum system at the same time. Or another way to put that is no two electrons. That's the particle we're referring to in this context. No two electrons can have the same four quantum numbers. Yeah. Okay, and then you also have Hund's rule. Hund's rule refers to a set of rules that the German physicist Friedrich Hund in 1927 stated, and put simply, they put that the electrons fill the giant orbital singly before they pair. You can look up the technical descriptions of Hund's rules, but that's not necessary for this class. Just understand what he's saying, the essence of what he's saying. Keep in mind, ladies and gentlemen, that the learning journey is, like I said, a journey. Be patient with yourself. Practice problems intentionally to improve your acumen and skill. That's where we're going to end off today. Hopefully you learned something, and if not, go back and just re-listen to the video, take notes. We will discuss new ideas in the lecture. We will really hammer in the Pauli's exclusion principle, Hund's rule, Heisenberg uncertainty, and we will tie that to the electron configuration. As we practiced last in class, we discussed Bohr model, and we did Bohr models. We wrote Bohr models from boron, carbon, nitrogen, oxygen, fluorine, and neon. And I gave you the Bohr packet, Bohr model packet. So just practice your problems, go through the homework, and really understand what's going on. So it's good to have you, good to see you in class, and I hope you are doing well. This is the end of the lecture.